So this work, it's a coupling between GeoClaw and Sphinx for far field tsunami inundation forecasting for Colombia, and this was an work that started last year with the Kamchatka earthquake and tsunami. Given the problems that we had with time computation for far field tsunamis. And so this is a collaboration between some colleagues, Ronald, Juan, from the General Maritime Directorate in Colombia, and then Maria Paula and me here. So as you may know, Colombia is located here in the north part of South America. We have local sources for tsunamis, but also we have several and more probable far field tsunami hazards. So we don't have that information about the risk related to those far field hazards, but also we didn't know. But then, as I said, what was the impact that an eventual tsunami coming from Kamchatka were going to have? It was going to have. So for some context, we have local seismic and tsunami hazard. We have one of the top 10 earthquakes in the human records. It was the 1906 earthquake and tsunami, which magnitude is calculated about 8.8. And I see that we have some colleagues from Ecuador here, so they can relate to this event. And it was in the border between Ecuador and Colombia. And just for context, it was registered in several newspapers in the US, such as, for example, here for the Oregonians, in the Morning Astorian. And they talk about the terrible earthquake and the consequent tidal wave, as it was called by that time, that hit Colombian coast. So, and also we had another tsunami in the 1979, magnitude calculated. There is a lot of several publications talking about magnitudes between 7.9 and 8.1. And these are some of the pictures that show the destruction and the inundation related to that local event in the 79. Tumaco is one of the most vulnerable populations. So it is close to the border with Ecuador over here in this red square. And when you zoom into this island, you can see the high exposure that these people have, more than 100,000 people living in this small island with no place to evacuate. So of course we are worried, and the national authorities are worried. And when you see the numbers, we have a high exposure. We are talking about that specific place where they have more in total with the surrounding local small places. We have more than 200,000 people exposed. So you can understand what is the idea here. So in terms of what we have is that we have some sources. We have a worst case scenario that we use for deterministic hazard assessment. That is the one that you can see where my mouse is. And that is basically the combination of the two previous events that I showed before, the 1906 and the 1979, based on what we have for data and information. So based on these events, we have the National Tsunami Warning Center in Colombia that works as most of the warning centers in the world do. So we have the seismic data coming from the National Institute, the Geological Survey of Colombia. Then this seismic data goes into the Tsunami Hazard Assessment Framework for the National Authority, for the National Maritime Authority, which calculates and computes the possible tsunami that can generate a warning. So what they do is basically to compare this type of earthquake coming from the geological survey to one of the database pre-computed simulations. And you can see some of the epicenters of these, some of the locations of the pre-computed earthquakes and tsunamis. And then based on that, warning is generated. And then what we want to do is to do the same for far-field tsunamis, to have a better understanding of the Pacific Basin, and then have a database of regional and far-field scenarios. So now I'm going to hand this over Maria, so she can continue with the presentation.
Thank you, Eric. Okay, I'll present the coupling framework we developed between GeoCloud and Sphinx for five tsunamis modeling along the Colombian Pacific coast and the main results obtained about that. First, in terms of methodology, the approach is based on leveraging the strengths of each model at different spatial scales. GeoCloud was used to simulate tsunami propagation from the seismic source all the way to the Colombian Pacific coast. In this context, the use of adaptive mesh refinement of GeoCloud is key as it dynamically refines the computational grid in regions where the solution becomes more complex, while maintaining a cursor resolutions everywhere. This allows us to accurately capture the evolution of the tsunami wave trained at the ocean scale while maintaining a reasonable computational cost. Sphinx, on the other hand, was used for high-resolution coastal modeling and indentation across the 11 selecting communities. Due to the simplified physical formulation of the model Sphinx, it is possible to run simulation at very high resolution with very low computational times, while still achieving a good representation of water levels and inundation depths, which is the focus of this project. The coupling between both models is implemented in one-way approach. At the intermediate coastal domain that connects GeoCloud and Sphinx, 10 observation points were defined. At these locations, GeoCloud records the temporal evolution of sea surface elevation as well as the momentum components throughout the entire simulation. For Sphinx, we only use the sea surface elevation. These resulting sea level times series are then imposed as boundary conditions in Sphinx, acting as the forcing that drives tsunami propagation within the coastal domain. In this way, the signal generated and propagated by GeoCloud is directly transferred into the local model, which is a GeoCloud, a Sphinx, sorry. Next, please. Moving on the model configuration, several scientific analyses were carried out for both models to determine which is the best configuration. For GeoCloud, the spatial resolution was identified as the most critical parameter. Cursor resolutions fail to properly reproduce both the phase and amplitude of the tsunami signal. As we will see later, in the results, while finer resolution significantly improve model performance, although it is balanced with the expense of higher computational cost. Additional, the Manning coefficient and the refinement data wave tolerance were found to have a strong influence in the results. Based on this sensitive analysis, the final configuration included 3 flag regions and 4 refinement levels, reasonable resolution from approximately 7 kilometers in the open ocean down to about 100 meters to the Colombian coastline. For Sphinx, the subgrid approach was used with a base grid resolution of 30 meters and a refinement level of 6, achieving effective resolutions of around 5 meters in areas with complex morphology, which with that we can obtain a higher resolution in some areas that are really complex in these zones of the Pacific coast. In terms of computational efficiency, GeoCloud simulations required approximately 1.5 hours, while Sphinx simulations took about 1 minute per community, resulting in a total of roughly 10 to 12 minutes for 11 study areas we selected to evaluate all the tsunami hazard for far-field tsunamis. For validation, observations were used at 2 different scales. In deep water, GeoCloud results were compared against the dark South Acapulco buoy, while at the local scale, the Doppler resolution results were validated using the Tumaco tide wave, which is located over here in the map. Next, please. Well, the case study used for validated the coupling of these two models was the 2025 Kamchatka earthquake with magnitude approximately by 8.8. This represents an ideal far-field event with available measurements both in the open ocean and at the coast. Two different seismic sources were analyzed, the USG Fall Model version 3 and next the NOAA SIFT base source. Next presentation, please. Both sources reproduce the overall tsunami propagation, but they differ in the spatial distribution of the initial seafloor deformation, which leads to difference in the simulated signal, as we're going to see later. Well, for the open ocean validation of the GeoCloud model, the importance of the spatial resolutions becomes very clear in this time series. With a coarse resolution of approximately 22 kilometers, the models fails to reproduce both the phase and magnitude of the tsunami, resulting in temporal shifts and amplitude underestimation, which is the purple line of the time series, as we can see in the presentation. When the resolution is increased to around 7 kilometers, which is the red line in the time series, the agreement improves significantly, especially for the SIFT source, which shows the best overall statistical performance. Additionally, during the 3 to 4 hours after the tsunami arrival at the DART, the simulations consistently reproduce the phase, the temporal sequencing of the oscillations, and the relative amplitude of the dominant cycle, especially to the highest energy waves. And after approximately 16 hours of the occurrence of the event, a larger dispersion in the results is observed, although a general consistency in amplitude is still maintained. Next. Regarding to the local validation of the GeoCloud and Sphinx coupling, the results shows good agreement in general in the reproduction of the initial tsunami phases and the maximum amplitudes, particularly during the first 19 hours of the event. We can see in the presentation. The SIFT source shows a slight overestimation of the amplitudes, but overall provides a better statistical fit compared to the USG source. It is important to know that in the time series, that due to the location of the Tumaco tide gauge, the observed signal contains high frequency noise that couldn't be completely removed. This noise is mainly associated with local effects such as reflection from the pyrite structure, where is located the void, and internal dynamics within the Tumaco Bay, which introduce some uncertainty in the comparisons. But in a general way, we see a good fit of the coupling of GeoCloud and Sphinx with the file data we observed. Next. In terms of spatial results, the Kamchatka tsunami generated relative low wave heights along the Pacific Colombian coast. This is partly due to the fact that the tsunami arrived during low tide condition with limited inland penetration. But in any case, we can see that in the area of Tumaco, there are two clearly areas with higher hazard levels, which is El Bajito and El Morro Beach, where the highest amplitudes are concentrated. And we can see that in the presentation. And once the coupling framework was validated, the simulations were extended to the remaining coastal communities, the other 11 study areas, allowing for a regional assessment of tsunami response along the Colombian Pacific coast. We have some troubles with the boundaries of the Sphinx model, and we can resolve it increasing the resolution of the geocloud model in the intermediate domain of geocloud and Sphinx. Next, please. And yeah, that's the 11 communities we simulate with this framework. And in summary, we can conclude that geocloud and Sphinx coupling provides an efficient framework to integrate ocean scale propagation with high resolution coastal inundation modeling with intermediate cost of computational efficiency. The seed source showed the best agreement with the ghost operation, and from the geocloud perspective, the model is highly sensitive to spatial resolution. And we see that increasing resolution improves the quality of the results, but also significantly increases the computational cost. Therefore, a key aspect of this work was finding a balance between accuracy and computational efficiency, which is essential for rapid assessment application. And finally, under this coupling framework, we have advanced in the simulation of worst-case rupture scenarios across 25 seismic coupling segments distributed along the Pacific coast, providing a basis for a more comprehensive far-field tsunami hazard assessment. And what we want to do is to use this coupling framework to evaluate several probabilistic cases of tsunami far fields along the Pacific coast.